recording on the cloud, so that's cool. Okay, yes, thank you everyone. So thank you for coming back. First we have and I handed out the survey, so please fill it out, or there's a QR code so you can fill it out online as well. Thank you.
Thank you. This talk is an advertisement for a research problem area of building fast dictionaries that support successor queries, and this is in the on disk setting. All right, we've already seen in a couple of different talks what a dictionary is, and specifically I'm going to be looking at dictionaries with support successor queries. So this is find me the next key that's present in the dictionary that follows this query key in some specified sort order for the keys. Now, there's a pretty obvious trade-off between the performance of insertions or updates to the dictionary and queries to the dictionary. This kind of just is natural because the more time you spend organizing your data when updating the dictionary, the less time you'll need to do to find that data later on when you go to query it. And if you spend less time during insertions, you'll have to pay more during queries. And so the research program that I'm interested in is, let's try to make dictionaries that have insertions that are as fast as we possibly can make them, while preserving fast point queries, and I'll have a more technical definition for that in a bit. And the thing that I'm particularly interested in this talk is also preserving some sort of a reasonable performance for successor queries. And I'm going to be analyzing dictionaries in the disk access machine model. So I think many people have also seen this, but just to go over it very quickly, we're going to have a cache of size m words, and we'll have a disk, and you have to move data from disk into RAM to operate upon it. I'll use RAM or cache interchangeably. And you move data between disk and cache in blocks of size B words. And the goal in this model of an algorithm or data structure designer is to just minimize the number of block transfers. So this model, for example, ignores CPU. You can do a separate analysis to ignore CPU, and then you combine those to get a more global picture of your algorithm. But for many algorithms and data structures where the I/O is the dominant term, this is a very powerful tool for analyzing. So that's what we're going to use. Now, B trees are a classic data structure. Again, I think we've seen presentations of this today, so I won't spend a whole lot of time on it. But the idea is we're going to size each node of the tree to fit within one block. So we'll use all that space in the internal nodes to store pivots to direct our searches to subtrees. So we'll get a really high fan out, and therefore we'll get a very low tree depth. And so that's going to reduce the number of IOs to do basically all operations, because every operation in the B tree is just a root to leaf walk. That's queries, inserts, successors, everything. So all these operations cost log base B of n, and scans cost log base B of n to find the first thing, and then you can just read your L items that you want pretty much at disk bandwidth after that. And so this could be a common pattern where we see the successor, the scans basically have a startup cost and then read them. Okay, so B trees were thought to be optimal, and in some sense they are for a certain range of parameters. But starting about 25 years ago, people started poking at this, and Brodel and Fagerberg proved some really interesting theorems in an atomic key comparison model. And so what that means is we're not going to be using hashing here, we're just going to be comparing the keys and treating them as atomic units. And they gave three different matching lower and upper bounds on the trade-off between insertion performance and point query performance in a dictionary. And so they're all expressed as if your inserts cost tau IOs, then your queries have to cost at least some function f of tau. And I'll show this to you graphically. So here's going to be the x-axis is going to be the insertion cost tau, and the y-axis will be the query cost. And this graph is absolutely lovingly ripped off from their paper. So I'm going to give them full credit for what I'm about to show you. If you have sufficiently expensive insertions, then you can get sufficiently cheap queries. This is just the classic B tree right here. On the other hand, if you ask for insertions that are super duper cheap, and don't sit here trying to parse this, just basically means if you don't even give yourself enough time to sort the data, then you get some really, really expensive query time, and don't bother parsing that very carefully. it just basically means it's polynomial time, like root of n or something like that time to do a query. And for me, that's not going to be really fast queries. But in the middle is this interesting thing where if you can get insertions that are noticed that the average IO cost to do an insertion is less than one over like log cubed n, all the way down to this log of the 1 plus epsilon of n divided by b. And so you can get these very cheap insertions, much cheaper than a B tree, but you still get roughly logarithmic query time. It's a different base to the log, but it's still going to be pretty fast. And they gave a construction that actually meets this, which is colloquially known as the epsilon tree. So this is exciting. Much faster insertions, still really fast queries, point queries. Whoops, okay, I used to call this the buffered B tree, but changed my mind. Okay, so let me show you B to the epsilon trees because they're going to have a really important idea at their heart that we're going to be using a lot the rest of the time. So again, it's going to be a search tree where we're going to size each node to fit into one block, but we're going to use the space within a node differently. So rather than using all the space in a node to store pivots, we're only going to have a small number of F of pivots. And then we'll use the rest of the space as buffer space for new insertions into the tree. And so think here that F is going to be much, much smaller than B. The data structure actually works even when F is closer to B, but I want to look at it when F is smaller. So that means the fan out will be order F. That means the height will be log base F, so the tree is going to be taller. But let me show you how we're going to be able to make insertions faster. So when you insert a key value pair, you don't have to go root to leaf. You just put the key into the buffer at the root. And you keep doing this until that buffer fills up. And when that buffer fills up, then you just move those items down to the buffers of the child to which they're going. Now notice when I move things from a parent to a child, that's a constant number of IOs, right? And in fact, to flush everything in here is basically F IOs, just to read in all the children, copy everything over, and write things back out. And by doing F IOs, I got to move roughly B items one level down the tree. So the average batch size where we move something down the tree is B over F. And this batch size is going to be related to how much faster we make insertion. Because the total work to do insertions is, at the worst, you just have to move something all the way from the root all the way to a leaf. So you got to do log of F, move it down the tree one step. But every time you move it down the tree one step, it gets to share that IO with everybody else in its batch. So you get to divide by the batch size. And so that's why you get this as the insertion cost. Now the query cost is still just the root to leaf walk because it's still just a search tree. You do have to search in the buffers along the way, but that's more just CPU. That's no additional IO. And scans likewise have the same structure. You just have to do a search down the tree for the start of your sequence, but then you do get to read things out. It's a little bit more complicated. You have to merge things to the different buffers and yada yada. So really just kind of see exactly why this is so much faster than the B tree. Here's the bounds that I showed you a minute ago. Here is if you take F to be B to the epsilon, what you get for those bounds. And here's if you take, and that's why it's called the B to the epsilon tree. And if you take, for example, epsilon equal to a half, what you get, for example, is you get log base B of n, technically log base square root of B, but that's just a constant factor off from log base B, divided by the square root of B. So this is a case where we're getting a square root of B speed up in insertions compared to a B tree. But again, we get log base square root of B for the query cost, which is again just a constant factor slower. So we're getting this massive square root of B speed up on insertion for only a constant factor slowdown on point queries. That's really exciting. And this works, I guess this table didn't come out right. You know, in general, if you wanted to match the Brodel-Fagerberg lower bound, you would take the fan out to be tau times B over log n. That would give you an insertion cost of tau and all these other parameters, which is what matches the Brodel-Fagerberg lower bound, as long as tau is sufficiently large, log to the 1 plus log to the what something a little bit larger than 1 divided by. All right, so that was where things stood for a long time, and that's where they really are still. in terms of comparison-based dictionaries. But if you allow yourself to do hashing, then there's more recent results, which are really kind of broke up in a whole new avenue of design dictionaries. So this is the icon for Trashview lower bound. And here we're going to allow hashing. And they give a single, their bounds have the same form, but it's just one bound. So if your inserts cost tau, then your queries have to cost log base tau via them. So we can kind of visualize that in the same way. And their bounds hold for insertion cost less than 1 IO. If you allow yourself 1 IO, you can be happy. Even a little bit less than 1 IO, then this lower bound. And they give a construction that matches this lower bound all the way down to an insertion cost of log of it. Later on, Conway, Farage, Colton, and Shalane gave another construction, a simpler one called the bundle of trees, matched at the same. Now, just to kind of remind you of where we're going with this, remember the B epsilon tree in the comparison model only got it down to epsilon. But they got sort of an exponential improvement in how fast we could make insertion while still keeping logarithmic queries. But these constructions down here really are hash tables in every sense of the word, and you might think of the hash table of memory, which means in particular, there was no support for successor queries. Scan your data structure. That's how you did a successor query. So they would take linear time to use successor queries. Whereas remember that the epsilon tree still had logarithmic time to do a successor query. So what I want to tell you about today is some progress on trying to figure out how far we can push this. So I'm going to tell you about the map B to the epsilon tree, which pushes us into this hashing area and gets the insertion cost down to log over log log, which is a bit of an improvement over log to the 1 plus epsilon, and still has successor queries that they're not quite logarithmic, they're logarithmic with this extra cost factor in front, but this is still way, way better than scan your entire database buddy. Also, in practice, this is actually pretty good. So for example, you could plug in some numbers. If n were 1 billion, then, and say we made this like 1.1, we just made it a little bit larger than log of n, then this would be like 40. This would be about 6. And this exponentially smaller thing would be 5. So in practice, this is pretty good. Now we're going to get to the map to the epsilon tree in 2 steps. The first, I'll show you the size tiered B to the epsilon tree. That's going to have faster insertions, but it's going to have slower queries. And then we'll do the map to the epsilon tree where we fix the query. And this idea of size tiering goes back to this paper 97, where it was called step merging in LSM trees. And I just want to cite them because I think they've kind of forgotten. Okay, so remember, here was the structure of a node in the epsilon tree. We had some buffer space, we had some pivots. And remember what this got us was that our flushing size, we flushed B items using FIS. And that was the key to accelerating insertions. So if we're going to make insertions faster, we're going to have to figure out a way to flush more stuff with less IO or the same amount of IO or same stuff with less IO. So we're going to need a new node structure to enable us to do that. This is going to be the node structure for a size tiered B to the epsilon tree. Each node will actually consist of several blocks. One block that just has a bunch of pivots. So we're still going to have a fan out of F, which means that most of this block will be wasted space, but I don't care. And then there'll be several buffers attached to this pivot block. There'll be up to F of these buffer blocks. Each of them will be 1 block. And the goal, as I'll show you in a minute, is this is going to let us flush FB items using FI. Okay, so how is flushing going to work? Now, these buffers have no sorting relationship with each other. Within the buffer, your items could be sorted, but between buffers, there's no sorting relationship. first thing we're going to do is we're going to take all these buffers that we want to merge from the parent and sort them into a bunch of output buffers. And then we're just going to attach all those output buffers to their corresponding chunks. That's a flush. Now, the really important thing to observe is that all the old buffers at the children didn't get touched at all. We didn't have to do any IO to access them during this flush. And so now to compute the IO cost of a flush, we'll just count all the things that didn't gray out. There's F of these pivot blocks, there's F of these new blocks, there's F of these old blocks. It's FIOs, order FIOs. And how many items do we flush? We flushed F times B items. That's how we got this bigger batching factor. Okay, so how does that look in the overall tree? So here's a cartoon of a bigger size here, be the epsilon tree. The fan node is F, so the height is still log F. The flushing size is order FB using FIOs. And so therefore, by a very similar argument from before, we're now going to have insertions that run in log of F divided by B. Log base F divided by B. Whereas before, we had top of B. So we split up insertions. Now the downside is when you do a point query, you still have to do this root to leaf walk, but now you have to search in all of these buffers. And there are up to F buffers per node. So point queries just got F times work. And scans also got F times work. At least the startup cost for a scan, not the long range. Okay. So we succeeded faster, but we made the query slower. So now we want to fix the query. And to do that, we're going to build a maplet. And a maplet is a generalization of a data structure called a filter. So filters, when I say filter here, I mean some things like Bloom filters or cuckoo filters or quotient filters or yada yada. So these are data structures for representing a data set in a very compact way, but with possible errors. And so most filters represent a set, but a maplet is going to represent a map in a compact but lossy way. So when you query a maplet for a key K, you're going to get back some set of values V that might be associated with K. And maplets may have false positives, which means that when you query for a key K, you're definitely going to get all the true values that are associated with K, but you may get some extra values thrown in for fun. And the false positive rate of a maplet is defined to be the average number of extra values that you get in your set. There's a very simple implementation of a maplet you can build based on ideas from quotient filters. You just use a linear probing hash table, something like this, where you store every cell of your hash table can contain a single hash of a key and a value that's associated with that hash. And so now you just, to do a lookup, you just scan, you just do a standard linear probing query. And you can save space in this hash table by eliminating some of the bits using a technique called quotienting, which goes back to Knuth. So just as an example, if you were to make the query for Knuth, then you access the 28, that part of your hash table, you start scanning, you find all the 28s, you return all those values, so the result is the set 7. That's how a maplet works. And the reason to walk through that example is just to kind of make it very obvious that if this maplet is an external memory dictionary, then queries cost a constant number of IOs because you just have to go to one local position in the table and scan a short distance for it. Okay. Now let me show you how we're going to use maplet to fix the query problem in the size 2 video. The basic idea is that each of these nodes is going to have its pivots and the buffers that I showed you before, and now it's going to have a maplet as well. And what the maplet is going to do is when you query for a key, it's going to tell you which of the buffers might contain that key. And so now instead of having to search all these buffers, you're just going to query the maplet and then search the buffers in it. So for example, that means the IO that you'll have to do, you'll have to access the pivots page. You'll have to do order 1 IO to access the maplet. And that maplet will configure it to have order 1 false positives. Will tell you if any correct buffer you have to look in, plus maybe like one extra buffer. And so as a result, you're going to access a total of a constant number of blocks per node that you visit during your query. And so that means point queries are now going to be back down to the height of the tree, log base F. And now scans didn't get any better because the maplet can only answer point queries. It can't tell us anything else. So we're stuck with. Now, what about flushes? So we've added this maplet data structure, but we have to maintain it. So every time we flush a new buffer to a node, we have to update the maplet to now map all these keys to say, well, you know, these keys you now have to look in this buffer as well. And so you might worry, is that maplet maintenance going to screw up the insertion node complexity for the data structure? And there's just a bunch of algebra to getting through to showing you that it does not. But I'm just going to say for this talk, it does not. Maplet maintenance is not a bottleneck to achieving Iacona-Petrasco optimality, and it's also not a bottleneck in practice. And sort of for very different reasons. It's not a bottleneck to optimality because the data structure is actually optimal when the maplet is the bottleneck. So you might imagine that sorting the data is the bottleneck in some configurations and maintaining the maplet is the bottleneck in others. Turns out it's when the maplet is the bottleneck that the data structure is optimal, which is very surprising and a little bit weird to me. But in practice, your key value pairs are much larger than the word. The maplet, each entry in the maplet is only a few bits. So the maplets are so much smaller than the data in practice that for that reason, they're not a bottleneck to maintaining the data. And so we can prove the theorem that this data structure meets the Iacona-Petrasco lower bounds whenever the fan out is log over log. And then you can also prove that you get the Iacona-Petrasco that was mentioned at the beginning of the talk. So there's one interesting observation I want to make here is, you know, there was this sharp divide between comparison-based and hashing-based dictionaries, right? And, you know, there were comparison-based dictionaries that supported logarithmic successor queries. And there were hashing-based dictionaries that went all in on hashing. They did nothing that was comparison-based. And they had linear time successor queries. And this data structure is going to be optimal for the inserts and point queries, and it's still going to have successor queries that are relatively efficient. And the way it accomplishes that is it's mostly a comparison-based dictionary with this one little bit of hashing stuck onto the side, which I think is kind of like, how little hashing do you need to use to get optimality in these really low insert cost regimes? So at this point, we've achieved some progress in the goal, but obviously there's open questions of how much further can we push this. So we've got optimal inserts and query trade-off, and we have reasonable costs for successor. I think I have time to show you a experimental thing. So we implemented this in a system called SplinterDB. And then we plugged it into Postgres, which is an SQL relational database that has a built-in B tree. And then we ran a bunch of workloads and we compared the performance of those workloads using a B tree as an index versus using SplinterDB as an index. So this first benchmark is showing insertion throughput, just inserting random records into Postgres using 3 different types of indices. The top gray line is no index whatsoever. So if you wanted to do a query later on, you would have to scan the database. The green line is the B tree, which does the classic B tree thing of falling off a cliff once the data set no longer fits in memory. And the pink line is SplinterDB, which shows that it doesn't fall off the cliff, but it does oscillate as it occasionally has to stop and do these flushes that I've been talking about. And so once the database gets sufficiently large, Splinter is about 18 times faster than the B tree, and is surprisingly only about half as fast as not keeping any index at all. So I think it's surprisingly good. So this demonstrates that we really are getting much, much faster inserts. Now here is the part of the talk where I introduce concurrency and parallelism. So this is random queries in the database. And So in theory, what the theory said is we might have slower queries because the height of the trees got taller. What this shows is that in practice, that doesn't happen. In practice, the point queries for SplinterDB and the B tree were exactly the same. And this is for any level of concurrency. So there, this talk now fits into this. There's actually a ton of concurrency stuff that goes on inside of SplinterDB, but it wasn't what I wanted to focus on this talk. But if you want to talk about it, I'll point it out. Now here's the interesting thing. This is plotting in throughput. Where this is throughput, this is the size of the scan. Remember, scans had a startup cost plus L over B. So this is L. The x-axis is what value of L we were using. And remember, these the map, the epsilon tree has a higher startup cost. So you would expect for short scans that it would in fact be slower than the B tree. And that's what we see. But then once your scans get sufficiently long, then we see that Splinter, the map to the epsilon tree, is actually faster than the B tree. Anyone here an expert on B trees might want to make a guess as to why it actually really is faster? That's not noise. So B trees do splitting and merging of nodes. And so on average, a B tree node is not actually full. When you read a B tree node, you don't get the item. On average, you get about 3/4. And so that's what's killing. That's what's limiting the performance of this B tree. And on Splinter, all these buffers are absolutely packed full. There's no empty space. And so it's getting the full discount out of the range query. So that's it. I hope I've got you intrigued by this problem of how far can we push this insertion cost down while keeping good point queries and supporting some kind of don't scan your entire database successor queries. I think there's really 3 basic open questions. Can we make the insertions faster? Maplets are not the bottleneck. Can we improve successor query cost? Right now, we're paying this higher than we would like startup cost in successor queries. People that propose range filters, can we do something with range maplets? Maybe there's actual cascading. I really have no idea how to tackle this problem, but it would be great if we could. And of course, can we get lower bounds on successor queries that help us know how well we're actually doing? Thanks for listening. Okay. Yes. So most B trees have an optimization to try to detect that kind of situation, and they'll be fully packed up. And in fact, so all the buffers, since all the buffers in a map B, the epsilon tree or Splinter, they're statically built. We just statically build them to be all full. No idea, that was done last week. That's interesting. So part of the problem with the startup cost is that even if you could predict where the actual successor was, there's so many different buffers on that route to the path. Like if you wanted to do a range query that was only 7 steps long, it really could be that every one of the first 7 things in that range were in different buffers. And then there's just nothing you can do. No additional indexing information could avoid that IO in the current structure. But I think the real workloads may not have that property. And so I think that's a good direction.
It's when you start looking past the original insights. Start looking at success. Why is that for the next year? What are other?
That's an interesting question. Well, successor queries are things people actually use. You know, this is what successor queries are, what analytical databases are all about. And so I think they're kind of the high nail that we had to figure out how to solve. After that, I would imagine it's to some degree taste, but personally to me, one of the really thorny problems is multidimensional index. That's really tough.